You have two parties, Alice and Bob, and one of these parties wants to prove something to the other. And in this talk, we're going to specifically focus on proving the results of some deterministic polynomial time computations. And here we'll ask for Alice to be able to verify this faster than just recomputing the computation herself. And we'll want Bob to just do about the same amount of work as computing the computation. And to facilitate the verification of this proof, Bob will have to do something extra in addition to just computing. And he'll attach some proof. And in general, this proof might be some more rounds of interaction, but we'll show how we can actually be just a single attached string. And the key questions that we'll be interested in are how many messages and rounds of interaction are required to prove a statement like this, and under what computational assumptions. So we'll look at what's known according to these two axes. So first of all, there is a 4-round protocol due to Killian that uses collision-resistant hash functions. And 22 years later, there is this protocol by Kalai, Raz, and Rothblum, which just assumes a sub-exponentially secure PIR and gets a 2-message protocol. And there's also a bunch of other protocols that get one message delegation, assuming much stronger assumptions. And also in this work we get a 1-message thing just from polynomially secure PIR. And also way up here almost off the charts, there's a bunch of work on interactive proofs, which are completely unconditional, but they require many rounds of interaction and therefore a restricted class of computations. And that's inherent to these unconditionally sound protocols. So our main theorem is that if you assume any succinct private information retrieval scheme, there is a 1-message delegation scheme in a public key model that has similar succinctness. So for example, if you have a PIR with polylogarithmic succinctness, then it will get a delegation scheme where the running time of the verifier and the sort of communication complexity of the whole protocol is also polylogarithmic in the time of the computation that you're delegating. And so for simplicity in this talk, we'll just assume that you have FHE, which is a significantly stronger assumption, but it'll make the talk simpler. And it'll still be polynomial time, FHE. So in that diagram before, the main challenge was getting to polynomial time assumptions. So just to be a little bit more explicit about what we get, I'll define this non-interactive delegation. So you have a worker and a client, and the client generates a public key and a verification key and sends a public key to the worker. At some later point in time, the worker gets some computation, computes output, and sends the result of the computation along with a proof to the client, who uses the verification key to look at the proof and decide whether or not he's going to accept. And then the worker can do this several times. And for soundness, we consider an adversarial worker. So that's something which has sort of corrupts everything in this reddish, orangish thing. So an adversary gets to see the public key and arbitrarily adaptively come up with some statement and a proof. And this adversary wins if he outputs some false statement and actually convinces the verifier to accept. And for soundness, we just require that for any bounded adversary, polynomially bounded adversary, that adversary will have just a negligible probability of winning. And I want to emphasize that this adversary is not allowed to see whether or not the verifier accepts. So this is something that's known as the verifier rejection problem. In this scheme and related schemes in our protocol, if you have a prover which is able to repeatedly just look at whether or not the verifier accepts some malformed proofs, he will actually be able to eventually come up with a proof of an incorrect statement. And this is a big open question in delegation to sort of solve this from standard assumptions. Okay, so the roadmap is we're going to modify this protocol of Kalai, Raz, and Rothblum in 2 steps. First, I'm going to talk about how we can get polynomial time assumptions. And then I'll talk about how we can make it a 1-message scheme. But first, I need to teach you some background information. So The scheme of KRR, I'm going to call it from now on, relies on this template of Aiello et al., which starts with a multi-prover interactive proof. So in a multi-prover interactive proof, instead of having a single prover, you have multiple non-communicating provers. And so the verifier sends a query to each one and receives an answer back from each one. And this model of having multiple non-interactive provers in general makes it easier to design a sound protocol. And in fact, complexity theorists have studied this and come up with many beautiful proofs in this type of proof system. And so the idea of Aiello et al. Was to try to take something like this and turn it into a single prover argument scheme in the following simple way. So instead of sending k queries to k different provers, you just take these k queries and encrypt them under independent FHE keys. And now, using the functionality of FHE, a single worker can just act as these k different provers. And the idea is that because the queries are under independent keys, the prover is somehow forced to keep things separate. But this is a little bit too imprecise, so let's zoom in a little bit. So in MIPs, we're guaranteed soundness as long as these answers are generated locally. So each query, or each answer, is just a possibly randomized function of a corresponding query. And on the other hand, what semantic security of an FHE scheme gives you is something is a little bit weaker, called no signaling, which essentially states that the distribution of some set of answers is like independent of the queries that it's not supposed to depend on once you condition on the queries that it is supposed to depend on. And if you're seeing this for the first time, you might wonder, like, aren't these just the same thing? But the answer is no, they're very much not the same thing. And this sort of subtlety was pointed out by Dwork, Lindberg, Nauer, Nassim, and Reingold. And I'll just throw up the definitions of no signaling and local again for reference. And there's actually a pretty simple example of a no signaling strategy which is not local. So if you've ever heard of the CHSH game, this is it. You have some prover and it's given as inputs 2 bits. And what it outputs is 2 uniformly random bits subject to the constraint that these output bits are like a secret share or an additive secret sharing of the AND of the 2 input bits. And so because it's outputting a random secret sharing of something, you know that A1 by itself is going to be uniformly random, and so is A2. So the distribution of either A1 or A2 doesn't reveal anything about either of the queries. So that's just a definition of no signaling. It's easy to say that it achieves that. And also, if you kind of, by inspection, or actually the CHSH inequality says that it's impossible for local provers to actually coordinate their answers in a way that always gives you the correct XOR of the of A1 and A2. So this is just an example that no signaling strategies are in general something much bigger, the larger class of cheating provers than local provers. So with that said, for a while the state of the world looked like this. We had these MIPs that we know to be sound against local provers. And we also knew that FHE could force a single prover to act as a sort of no signaling prover. And the variant of FHE that you need depends on the variant of no signaling that you want. But there was still a mismatch. You couldn't actually instantiate this scheme for a while. And one approach to get around this is to try to introduce an FHE scheme that actually forces a prover to act locally. And this is done by Betansky and Kesa, and in a different work by Doda, Salovey, Rothblum, and Wicks. But these sorts of things rely on very strong assumptions. And the other potential approach, which was taken by Kalairaz and Rothblum, was to build an MIP that is actually secure against this larger class of cheating provers. And in this work, we show, to reduce the assumptions to polynomial time, we show that that same MIP is actually secure against an even larger class of provers, which we call these computationally no signaling provers. And computationally no signaling just means that when you had those two distributions that are supposed to be like the same, like independent of some other query that's not supposed to matter, now those two distributions just need to be computationally indistinguishable. And also we show that the MIP is adaptive, but we'll talk more about that later. Okay. So are there any questions so far? Okay. So now we're going to talk about how to show that the KRR MIP is actually secure against computational no signaling provers. And I mean, the basic form of the analysis is you say if you have a cheating prover, then it must be signaling. So we start with some cheating prover that wins with non-negligible probability, and we want to say this prover has to be signaling. And for the polynomial time assumptions, we want this prover to actually be computationally signaling. So the way that the analysis of KRR works is that first you amplify this prover to be a prover that wins with almost 1 minus negligible probability, but against a slightly different verifier, which I'll describe the difference between the real verifier and the relaxed verifier later. But you amplify this cheating prover to be a very strong prover against a different scheme. And then you show that for this scheme, any prover which cheats with very high probability must be signaling. And then you want to map back and say that, well, if this amplified prover was signaling, then the original prover must have been signaling too. So the analysis that shows that this prover, the very strong prover against the relaxed scheme must be signaling is like the core analysis at the very heart of KRR. And in fact, you'll have to trust me that that analysis, you just look at it and you'll just observe that it turns out that this prover must actually be computationally signaling. But this arrow going from right to left does not imply that the original prover was computationally signaling. And the reason is that the transformation from the weak prover to the amplified very strong prover is actually inefficient. If you look at the proof of KRR, this amplified prover involves conditioning on some very rare events, so it's just not efficient. And so what we want to do is to improve this soundness amplification step to make everything efficient, and we'll get our polynomial time assumptions. Okay. So I said there's a relaxed verifier and a regular verifier. So the regular verifier in KRR, it basically has a bunch of tests that it wants to do, and it repeats these tests lambda times independently, the same test, or lambda is some sort of security parameter, and it checks that all of those tests have to pass. Whereas the relaxed verifier does the same thing, but only checks that most of the tests pass. And so like I said we want to take something which convinces the regular verifier with non-negligible probability and turn it into something which convinces the relaxed verifier with very high probability. And we want this to preserve the efficiency of the cheating provers. And it turns out that in addition to getting the polynomial time computational assumptions, it's also important that this prover, this amplified prover, is polynomial time when you're delegating RAM computations, because in RAM computations you'll have some database which is compressed using a collision-resistant hash function, and you use the amplified prover to break the collision-resistant hash function. So if the amplified prover is inefficient, then you get no guarantees, essentially. So I want to describe the efficient amplification now. So we start with this weak prover, and we construct an amplified prover. So I'm describing the amplified prover. The amplified prover gets lambda different queries from the verifier. Each one of these queries I'm thinking of as corresponding to one of these repeated tests the verifier does. And then the amplified prover will, in his head, simulate another verifier. And he'll also sample a random permutation, which he'll use to mix these queries together in a random order and send them to the weak prover. So maybe you're wondering why the weak prover takes more queries as input than the amplified prover. And you just add some dummy provers to the weak prover that do the same thing, but it's not that important. So anyways, the amplified prover just will send a mix of the real queries from the verifier and some simulated queries to the weak prover and look at the answers that he gets back. And by hypothesis, the weak prover will make all of the tests pass with non-negligible probability. And by no signaling, that doesn't depend on whatever else you ask the weak prover. So it doesn't matter that the amplified prover is actually sending these verifier queries off on the side. And the amplified prover will then just repeat this process, repeat the simulation of the simulated verifier polynomially many times, enough to make sure that eventually, one of these times in his repetitions, he'll get all of the simulated verifier's answers to be good in the response that he gets from the weak prover. And once that happens, the amplified prover can send the rest of the answers, the ones that are actually supposed to correspond to the real verifier's queries, sends those back to the verifier. Yeah. So that's sort of I sort of mixed in the argument for why this convinces the relaxed verifier with high probability, because you can just repeat these queries to the weak verifier and do polynomial times. And I guess the reason is that the queries from the real verifier and the queries from the simulated verifier are completely indistinguishable to the weak prover. So if the weak prover is able to make all of the queries from the simulated verifier pass, then just a Chernoff type argument shows that most of the queries from the real verifier have to also pass when that happens with very high probability. And the efficiency of the amplified prover just follows from the fact that it runs the weak prover a polynomial number of times related to the weak prover's convincing probability. And in fact, it's easy to see that by like a hybrid argument, we can see that the amplified prover is in fact computationally no signaling if the weak prover was computationally no signaling, which is what we wanted to get. And it basically just is because the amplified prover is efficient.
Yeah. So in KRR, then there wasn't this explicit subroutine. It was like conditioning some randomized function.
It was conditioning. Not even just conditioning on the verifier convincing. It was conditioning on the prover convincing. It was conditioning on the prover outputting some particular proof string, or some particular output. So this is like a very low probability event, and and it wasn't important for the application of KRR because they didn't even need the prover to be efficient, or the.
It's here where it comes up.
Yeah. So anyways, this is a totally generic soundness amplification for in the no signaling setting when you have a bunch of repeated queries and you want to relax it to say that only most of them have to accept. I don't know how useful that is outside of this, but at least it's generic and it should make it easier to understand. So that's all I wanted to say about reducing the assumptions to be polynomial time assumptions. And now I want to talk about making it a one message scheme. So we have this. This is what our scheme looks like. And I'm going to say something. I'm going to say, let's just say that the first messages are a public key, and now it doesn't count. And now we have a one message scheme. And why is that okay? Well, so you probably have a few objections. First of all, if we're treating this first message as a public key, it really shouldn't depend on the statement that you're trying to prove. And it turns out that in many MIPs, including the KRR MIP, it actually doesn't. So that's OK. Other than, say, on like the running time of the computation, which it has to depend on. The second thing is, well, if you're going to advertise this as a public key scheme, an adversary had better be able to choose the computation adaptively based on the public key. And so this is a real challenge. And so I guess when we say that it's a one-message scheme, really what we're saying is that we show that the scheme is adaptively secure. So how do we do that? So the high-level view of how we do that is we look at an internal primitive of KRR, which I'll tell you about in a second. And I'll tell you that this internal primitive can actually be easily modified to an adaptive version. And then this primitive we'll use to achieve adaptive delegation. So the primitive is a proof of partial assignability, which I'll explain. So there's a lemma that's a little implicit in KRR and was abstracted out by Paneth and Rothblum, which says that if you have a prover for some statement, m of x equals y, and you can then build something called a partial assigner, which takes as input a set of variables. So we'll think about the computation transcript for this statement, m of x equals y, just like a list of all the Turing machine configurations. And the partial assigner takes as input a set of positions in this transcript and returns an assignment to those positions, such that if you look at that assignment within this transcript, they satisfy all of the local consistency constraints that you would expect if you take, say, a circuit that computes the transcript. Yeah, so local consistency, I'm not sure if I explained that very well, but you can take, say, the Cook-Levin circuit that computes a Turing machine, and each gate in that circuit is a local consistency constraint, and if the assignment contains assignments to any 3 wires that are part of the same gate, the values given to those wires have to satisfy that gate. And in addition, we want this partial assigner to be no signaling. In a sense, it's very analogous to what we talked about before. Namely, when the assignment that the partial assigner gives you to some set of variables doesn't depend on what other queries or what other variables you ask the prover. And the last thing I wanted to mention on this slide is that when I say a small set of variables, small is a parameter. We're talking about some MIP scheme, and this MIP scheme we can instantiate with some number of provers, you pick, and then you'll get a partial assigner where you can query on some number of variables that's about the same as the number of provers. So that parameter basically determines the communication complexity of everything. So you can have an adaptive version of this thing too, adaptive partial assignment generator. So now it's not a prover for any fixed computation, but still it'll take as input a set of variables, just indexing into some transcript where you don't even know what the computation is that the transcript is for. And the partial assigner outputs an assignment together with the computation. And again, you have this local consistency constraint, which is that if you look at the assignment that the assignment generator gave you as part of the computation transcript for some computation that it's telling you, the variables that, the assignment that it gave you satisfies all the local consistency constraints in that transcript. And the no signaling constraint, there's also no signaling constraint, and it's a little bit different now, but essentially if you think about the computation, the mxy that the assignment generator is giving you as just being the response to another dummy query that you ask the partial assignment generator, then it's the same notion of no signaling. So the distribution of MXY should be, at least computationally, independent of whatever queries you're asking this partial assigner. Okay. So once you have this thing, you can try to argue that it implies that the statements that this partial assignment generator is actually outputting are actually correct statements. So you can start by saying, supposing that you ask the partial assignment generator to give you the first layer of the computation, and it'll give you some configuration. It'll also give you M, X, and Y, and so you know by consistency that the configuration it gives you has to be consistent with, it has to actually be the first layer of this transcript, because the first layer of this transcript will probably have something that checks that the starting configuration is correct. And now if you imagine querying the first two layers, then you'll still have that the first layer is correct with respect to the computation that the assignment or output before, just by no signaling. If it was correct when you queried for the first layer by itself, it'll still be correct when you query for two layers. And by local consistency, you'll get that the second layer has to also be correct. And you can do the same thing. You can just sort of propagate this upwards. And eventually you'll get that when you ask for the output, it has to be equal to M of X, where M of X is whatever the prover outputs. But it also has to be equal to the claimed output by local consistency, because if you think about this computation transcript I said at the first layer, you'll probably have something which checks that the first configuration is correct, and then at the end you'll have something which checks that the output is what it's supposed to be. So you'll get by just transitivity that M of X equals Y. And that's really the whole proof. Once you have this partial assignment generator, it's quite easy to deduce global soundness. But I guess I want to go back and talk about, just briefly, the things that are important to be aware of in the subtleties. First of all, the properties that we looked at, we said that when you query the ith layer, you'll get the correct value. And in order to use no signaling to argue that is the same whether you query other things or not, it's important that the correctness is actually efficiently checkable. So I guess that's why it suffices to have a computationally no signaling assignment generator. And in terms of parameters, we were querying for whole layers, or 2 layers at a time, and that required us basically just everything to be as the communication complexity, the number of provers, to be as large as the space usage of your computation. But it's actually possible to reduce this with Merkle trees using Rizoliv, Klei, and Paneth. And okay, so that's everything I wanted to say about adaptivity. And in the few minutes I have remaining, I want to talk about something new, which is sort of succinct amortized NP delegation. So trying to delegate NP computations in a 2-message protocol with low communication complexity. So first of all, there are some barriers to, in general, succinct NP delegation. We know that if you're talking about unconditional soundness, then under some reasonable complexity theoretic assumptions, the total communication has to be at least a witness length. And you have essentially the same result for arguments if you restrict yourself to talking about non-interactive arguments and black box reductions to falsifiable assumptions, adaptive soundness, other stuff. But you can ask, can you do better? Can you get many for the price of one? And this problem was posed recently by Reingold and Rothblum. And for proofs, they showed that for a certain subclass of NP, unambiguous NP, you can have a proof where the communication is the size of a single witness plus the number of instances, roughly. It's a little different than that. And for arguments, in this book we show that we can do much better. For any NP language, you can just get communication that's proportional to a single witness. And it doesn't depend on the number of instances except for polylogarithmically, which I'm totally hiding. And there's a very simple reason for this. First, we're going to change the name to something a little bit cuter, a batch argument of knowledge. And the main tool that we're going to use is this notion of a partial assigner. So before we talked about assigners for some computation transcript, but in general, we can talk about assigners for 3CNF, a constraint satisfaction problem. And and we can actually prove a partial assignability of any 3CNF that is sufficiently structured. I'll gloss over what sufficiently structured means. But to build this batch argument of knowledge, we start with some CNF which has an input X hard-coded, and it'll take as input a witness and check that it's a valid witness. And we put a lot of these together just to make one giant CNF. And I just want to emphasize that these X's are fixed and not chosen adaptively, and seems inherent in this batch argument of knowledge that the instances are not chosen adaptively. But we can use this general protocol for proving partial assignability to show that this giant CNF has an M partial assigner, where M is the number of variables you're allowed to query, and we'll just set it to be a little bit larger than the size of a single witness. And so once you have an M assigner for this giant CNF, you have an M assigner for each individual CNF, and once you have an M assigner for each little CNF, you can basically use this reduction from local to global soundness that I talked about to see that each X must be in the language.
Where are you using this same relation in all the trees? In all the formulas?
Well, it's not important that it's the same relation in all the formulas, actually.
So it could be,
like,
so batch could be for different combinations.
Yeah.
Yeah. Very good.
As long as you know them.
Yeah, you have to know them ahead. But you don't. If the prover has to tell the verifier what they are, then trouble. So basically all that's going on here is that surprisingly, if you want to prove the partial assignability of some giant CNF, the communication complexity of doing that doesn't depend on the size of the CNF. It just depends on the locality, that the number of queries you want to be able to partially assign. And so then basically partial assignability amortizes really nicely. And I guess I just wanted to say a last thing before I'm almost done, I promise, is that even though we're just getting selective security here, we actually need to use the adaptive local to global technique because the assigner provides the witness, so it's kind of inherently adaptive. And yeah, if you want to know more, I guess you should look at the paper. But just to summarize, so we have this non-interactive delegation protocol from these sort of weak generic standard assumptions, and we look at this notion of an adaptive partial assigner, and we show that you can actually construct this efficiently, and there's a corresponding local to global argument, and these partial assigners they amortize really nicely, and you can use them to get batched arguments of knowledge for NP. And so if you want to know more, you can look at the paper.
Let me just make sure you answered my question. So if you go back 2 slides, so do you need RL to
Oops.
Do
Yeah.
you need RL to be the same in all the formulas or not?
No. I mean, because you can think of this as being like a sort of universal relation, and just X specifies the thing.
But even that you don't need. I think so long as you know, I mean, the
Yeah.
running time of the prover does not, you don't need to do like a reduction to SAP. It can like just compute the relation of the specific languages. I mean, you just need to know the circuit. This big and thing.
Wow. Very cool. Yeah. Great. Any questions?
So the gap with Gentry-Weeks now is very small.
Right. It's just.
So any hope to make it tight?
Well, not really. So Gentry-Weeks basically they use the fact that like if you could do something really succinct, then you could decide the language. You could decide whether all of these x's are in the language in time faster than you would expect. But here we're saying that you can already decide. You can decide whether all of the x's are in the language in time that's like k times 2 to the witness size. So basically the problem of checking whether many things are in the language is inherently easier, and that's why Gentry-Weeks doesn't apply here. So I don't think we have any ideas that are going to break the Gentry-Weeks lower bound.
It is tight. So you weren't asking about like overcoming Gentry-Weeks, right? You're just asking about getting. Yeah.
So the question is, it can either be extended to be non-adaptive, or it can either be extended to be
Right.
in the other.
So for this batch argument of knowledge, we actually I said that these x's are chosen non-adaptively, and that's inherent. If you could choose these x's adaptively, then we could build snarks. So.
Because of the other thing.
Yeah. Because basically, like one neat application of these batched arguments of knowledge is that you can use them to prove that a Merkle digest is honestly generated, and you actually know some large database that is a preimage of some Merkle hash, and then you can combine this with some RAM delegation protocol.
The only possible improvement is then to keep non-adaptivity and then get rid of the batched property.
Well, I guess so.
No, but it's not covered by Gentry-Weeks.
Right. I mean, so I personally, just based on like religion, think that Gentry-Weeks holds even in a non-adaptive setting, and so I would vote for that as the open problem.